Hello, this video is to discuss how to identify forces acting on a system and how to draw force diagrams. This is an incredibly important topic for physics. In fact, it's probably the single most, maybe the second most important skill in physics. Because our whole goal here is to make these mathematical models, and in this case, we're going to make this kind of graphical model, this kind of diagram to represent the physical world. And it turns out that like the heart of physics is about force, and the heart of mechanics. And so force is what we're going to talk about here today. Um, I do have a kind of a overview of how to do this process. I kind of called it solving equilibrium force problems. It should be in a unit packet that you've gotten from me. And so there's general steps here that we'll follow. The first one is to draw a sketch of the situation that you're dealing with. For our purposes, I'm just going to choose a sample situation. The situation I want to use is say, hey, let's imagine a nice snowy day, and we have maybe a child on a sled, right? And the sled's being pulled along with a rope by maybe some, older sibling pulling child along on a sled, and now we're going to have them pulled along faster, 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 faster to the right. Okay, that's the setup that we're going to go with here. And so that's the situation we're analyzing, is a child on a sled going faster, 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 faster to the right. So what we might do is draw a quick sketch of the situation so that people will be able to see later on what was it that we were trying to represent or model. What situation in the real world were we trying to analyze? So I'll just draw a quick little sketch and say, hey, look, I've got my sled. Maybe it's one of these sleds. I'm going to draw like a side view here. It's one of these kind of fancy toboggans, maybe. All right, there we go. On the ground, right? Let's see here. A child is sitting on the sled. Give that child one of those goofy little hats with the pom-poms. Here we go. Okay, and maybe they're sitting like this. The sketch does not have to be that fancy. All right, I'm exaggerating here for our purposes here, right? But we got this child sitting on the sled. Maybe they're hanging on for dear life. But anyway, yeah, rope, right? And this thing is going to the right, getting faster. Okay. Okay, and this arrow is to represent the velocity that we're moving to the right, getting faster. Okay, now the purpose of the sketch is so people can see what the situation is and remind myself what I'm analyzing. Sometimes sketches will let you see relationships between distances and lengths that you may not notice otherwise. For our purposes here, though, it's just going to be useful in seeing what's going on and helping us to do step 2, which is choosing the system. The system is what we are going to analyze the forces acting on in the motion of. In this case, we could analyze the child. We could make our system just the child, or we could analyze just the sled. Or because they're moving together, it might make sense to treat them as one big object and treat them as a combined system. For our purposes today, I'm going to do 2 for the price of 1. I'm going to do a diagram for the child and a diagram for the sled. And that's going to help us see some other things. So system is chosen, child and the sled as separate systems. What's common to do then is to, on the sketch, go ahead and draw what's called a system boundary, showing what's inside and what's outside the system. So this is just the child, and this is just the sled. Okay, it's 2 separate systems. Okay, so what comes next is drawing a force diagram. All right, and so what I'm going to do is I'm going to draw a diagram, a separate diagram for each system. And when I do this, I can choose to represent my system in a couple different ways. A very common way of doing that is to draw just a dot. So I'll represent the child with a dot, and I'll represent the sled with a dot. The dot is kind of representing the center of mass of the system. And so it's kind of, there is a meaning behind it. I like to draw my systems a little more complicated. I like to draw a box. if it's for most objects, and if it happens to be spherical, like a ball or a planet, then I'll draw a circle. But I like doing boxes for at least 3 reasons why I prefer boxes to dots, but dots are pretty darn traditional. And the dot does kind of give you this idea that we're treating the object as if all of its mass was focused at a point at its center of mass, which is indeed how we treat objects for first year physics. In second year, we worry more about how the matter is distributed as that affects the rotation of objects, but we're not going to worry about that right now. But I am nonetheless going to draw a box because, well, it's my video, and that's actually just what I prefer. So here, so we're on to step 3, drawing the force diagram. First, we're going to represent our system simply. So here, check it out. See this? This is the child, and this is the sled, right? And you say, again, why it makes this simple representation a box or a circle or a dot, a particle? Because the diagram we're about to draw, I want to make it very clear and easy to read. I don't want a lot of complexity. A lot of times, like, angles are going to be important, and I might need to even do a little bit of geometry on the sketch. So I want to make it as clean and clear as possible. The second thing that you'll notice about these diagrams is that I drew the child and I drew the sled, but they're not touching each other. Each diagram, you represent the system free from its surroundings. So it's kind of separated out from everything. That's going to let us see the force arrows and where they originate easier. It's also why force diagrams are sometimes called free body diagrams, because old-timey physics slang for object was body, and we're going to draw the object, the body, free from its surroundings. And so that's important. We don't do our diagrams on the original sketch. We draw them separate from the surroundings. You'll see as I go through why that's important. So next, I have to figure out which forces I have acting, and then I can need to draw them in and represent them on my diagram. So what I'm going to do here is I'm going to flip back and forth between talking about the different types of forces, and as I introduce each type, then I'll draw them in on the diagram and show you that. So first, and so the situation that I've chosen here is nice because it has just about all the forces that we're going to need to work with in first semester will be represented in this problem. So the next step, like I said, drawing force diagram, we need to represent our system. We're going to represent forces as arrows, but we got to figure out what forces are acting first. So we're going to use these how to identify forces on your system. This part here I've kind of expanded out a little bit larger here for you. How to identify forces acting on your system. And so basically I break forces into 2 main categories. The first one is ranged forces, and the other category is contact forces. So ranged forces, those would be forces that act between objects even though they're not in contact, they're not touching each other. Things like the gravitational force acts between objects, they may be very far apart, but they can still attract each other. Or electromagnetic forces or the nuclear forces act between particles in the nucleus of an atom, even though those particles may not in fact be in contact with each other. For our purposes, this year we are probably not going to do much with nuclear forces at all until the very last week or so of class. We may talk about it a little bit about nuclear forces as kind of a little side topic. So you don't need to worry about the nuclear forces for now. The electromagnetic force is something we will deal with a lot next semester. We deal with, because the electromagnetic force acts between objects that are electrically charged. And we'll deal with forces between electric charges next semester. Gravitational force, on the other hand, is something that's going to be involved in just about every problem we do. The gravitational force, you should know that it's an attractive force. It tries to always attract things together, so far as we know. And it acts between any objects that are made of matter, anything that's got mass. The gravitational force acts between them. This is Newton's definition we're using. And so you say, well, great, well, that means, will I have gravitational forces, for example, between the child and the sled? Would they attract each other by a gravitational force? And the truth is, yeah, they do. However, out of all these forces, the gravitational force is by far, far weaker than any of the other ranged forces. Like the difference between like the gravitational force, say between two protons in a helium nucleus, the gravitational force between them is something like, you know, 10 to the 39 or 10 to the 40th times smaller than the strong nuclear force between them. In fact, it's a bit of a mystery in physics why the gravitational force is so insanely weak compared to the other fundamental forces. So it turns out that in order for the gravitational force to be big enough for us to worry about, you have to have a just enormous amount of mass pulling gravitationally to make that force important enough to worry about. How much mass? Well, like a planet or a moon or a star. One of those two objects that force is acting between has to be just immense. Now, just about every problem that we do this semester, there will be an immensely massive object nearby, that being the Earth. And so we will have gravitational forces on just about every diagram that we draw because of the Earth being nearby. But I don't have to worry about the gravitational force between normal-sized objects because it's so incredibly weak compared to the rest of the forces we'll be dealing with. So, how to represent a force on a force diagram? Again, what I would say first is a force, our definition for a force is really, really important actually, and I can't believe I don't have that printed out here for you already. But our definition for what a force is, okay, we'll use a variable capital F generally to represent forces. We say it's an interaction between two objects that results in a push or a pull. When I was a wee lad, my science teachers used to say that force was a push or a pull. But this is a little bit more nuanced definition, and you'll see as we go through that it's actually way better. That it's an interaction between two things, and it results in push or pull between those things. The point being, you need two objects to have a force, and it's something that acts between the two of them. We'll come back to that. But that's the idea. So gravitational force, at least one of those two objects must be just incredibly massive for that force to be big enough for us to worry about this semester. So moving on, how do we represent forces? The way we represent forces, because we care very, very much about the direction of a force, we're going to represent forces with arrows. And the rule goes like this. When I do a diagram like this, instead of just doing a dot or a particle, when I represent with a box or a circle, the rules go like this. First, the arrow shows the direction that the system is being pushed or pulled. So which way this object is being pushed or pulled by the other object. Secondly, we're going to start our arrow at the point on the object where the force is acting. Now the thing with gravitational forces is you might ask, hey, wait, if I'm talking about a gravitational force on the child by the Earth, for example, you say, hey, what part of the Earth is pulling on the child? Well, every part of the Earth. What part of the child gets pulled on? Every part of the child. If I try to draw arrows for every little bit of gravity pulling on every little part of the child, it'd just be a big blur of red. So we're just going to draw one arrow from the center. If I had two objects with a gravitational force between them, maybe here's the Earth and here's the moon. Drawn not to scale up clearly. You say, well, there'll be a force that acts along the line between their middles. Right? And so there'll be a force, the Earth is going to get yanked on by the moon, and the moon gets yanked on by the Earth. That force acts between them. And so you say, well, do we have evidence that the moon is getting pulled on by the Earth? And you say, yeah, that gravitational attraction of the Earth is what keeps the moon from just continuing moving around, just flying off. That gravitational force is what keeps it in orbit, right? Do we have evidence that the Earth gets pulled on by the moon? And you say, well, of course we do, like the tides, for example. We know the Earth is tugging on the water on the near side of the Earth and on the water on the far side of the Earth. And the part that's closer gets tugged harder, and the part that's farther away gets tugged less, and that's what kind of tends to spread it out and create these tidal bulges, we call them, of water on either side. Anyway, but getting to our point, yes, there's a gravitational force that goes both ways between them. I'm going to label this F sub g. It's a force. What kind of force? A gravitational force. In physics, we use subscripts to represent, as like labels or tags we can put on variables to talk about what a little bit more about them. In this case, that the force is a gravitational force. So anyway, so moving on. So in this case, again, I'm going to draw an arrow that goes between the middles of the two objects. Well, the two objects pulling gravitationally here are the child and the Earth. So I'm going to draw an arrow from the center of the child towards the center of the Earth. You say, hey, which direction is that? Well, of course, that is the downward direction. In fact, that's how we define down, isn't it? The way that the Earth pulls on things is my gravitational force on the child by the Earth. Okay, next, what about the sled? Is there a gravitational force on the sled? You say, sure, the Earth is pulling on the sled, so I'll have a gravitational force on the sled by the Earth. And you say, well, wait a minute, I've got two arrows and they're both labeled the same. They're both gravitational forces. You say, but do you think the Earth pulls equally hard on the child and on the sled? And the answer is, well, probably not. So I really ought to give each force its own unique name. And so to do that, we're going to do what's called a double subscript or an on-by notation. So we're using that double subscript, that on-by notation. So that means this is a gravitational force that acts on the child by the Earth. So I'm going to write this as CE, on child by Earth. This is a gravitational force on the sled by the Earth, so I'll do subscript SE. There we go. Gravitational force on the sled by the Earth. Okay, moving on. That's the gravitational force. Now, the rest of these ranged forces, we said, we're not going to need to worry about for a while. Electromagnetic is only when I have charged objects. We're assuming they're neutrally charged. Nuclear forces are only inside the nucleus of atoms, is only where they're important, so we don't have to worry about that. So now we're going to move on to contact forces. And as the name would suggest, in order to have a contact force, the objects need to be in contact with each other. So the way to figure out the forces is to ask myself, hey, I'm going to list everything that's touching my system. And then for each thing that's touching my system, I'm going to run through this sequence of questions. So our first ranged force, our contact force rather, is called the normal force. And so it goes kind of like this. Let's say that I have this book. Now, is the Earth pulling on the book? You would say, yeah. How do you know? Well, if I let go, the book would get faster and faster and faster down as it gets pulled down by the Earth. And so there must be that gravitational force on the book by the Earth pulling down. Let's just invent a value. Let's say that this book is acted on by a force of 2 newtons, okay, a force, gravitational force on it by the Earth. Well, right now, you would say, hey, it's not getting faster and faster down. Why not? Well, there must be a force pushing up to balance it out. What's providing that upward force? And you'd say, well, that's the force from my hand. So I'm pushing up. Now, if it's not accelerating down, there must be a force pushing up. You say, well, if the Earth pulls down with 2 newtons of force, how hard must I be pushing up? And you say, well, I must be balancing it out. I must be pushing up with 2 newtons of force. What would happen if I pushed with less than 2 newtons and the Earth still pulls down with 2 newtons? Then it would get faster and faster down. What if I pushed up with more than 2 newtons while the Earth pulls down with 2? Well, it'd be unbalanced force and it would get faster and faster upward. For it to not change speeds, for it to have a constant velocity, those forces need to balance out. They need to add up to 0, 2 up and 2 down, balancing out to 0. And so that's the deal. A situation like that we say is in equilibrium, when the forces add to 0 and the motion is just a constant velocity like this. So we're fine with me pushing up with 2 newtons to balance out the Earth, but what if I set it down on the tabletop here? Is the book accelerating down? You say no, it's not changing speeds up or down, so it's got to be in equilibrium. The forces need to balance out. Is the Earth still pulling down? Yeah, well then something's pushing up with 2 newtons. What's pushing up with 2 newtons? The tabletop. You say, well, how does an inanimate object like a table push up? I understand how a person pushes up, but how does an object like the table push up? And how does it know how hard to push? If I add more weight, it pushes up a little bit harder to balance that out. If I remove the weight, now the table doesn't push up as hard. Again, somehow it knows how hard to push to balance out. How does it do that? Well, the answer is actually a little bit of chemistry. You may recall from your chemistry class that that objects are made up of charged particles. At the teeny tiny level, the particles that make up an atom, you say there's protons and neutrons that make up the nucleus of an atom. And then there's electrons that are moving around outside that nucleus. So see that little plus? That represents like a nucleus of an atom, sure, with all like the pluses and minuses, all the protons and, pluses and neutrals, protons and neutrons in that nucleus. Now, the electrons are negatively charged. They're attracted to the nucleus. They're moving around, and that's what keeps them from drifting off. But you see, those electrons are moving around in a kind of random pattern around them. You knew that, right? They don't go in little circles around the nucleus. They actually move in kind of a random way. Right? This region where you can find the electrons, they're kind of moving randomly, but they're most often in this space. We call that space the electron cloud, that region around the nucleus where the electrons can most likely be found. Well, if I took in a material like, say, the tabletop here, it's made up of a bunch of teeny tiny little atoms, right? And the atoms are attracted to each other and held together. One type of bonding that we talked about a lot in chemistry was what's called a covalent bond, where electrons are shared. So maybe this is a carbon atom with 6 protons and we'll just say it's carbon 12, 6 neutrons there. And you say, and around it we have then 6 electrons buzzing around. Well, look, here's the next carbon atom over with its electron cloud. Now, when these guys bond, they're two nonmetals, they share electrons. They share some of their outermost electrons, their valence electrons. Now, those electrons that are being shared, did you know that they tend to spend more time in the space between the two nuclei? And those electron clouds kind of overlap a little bit when they form that bond. Now, all this hopefully is somewhat familiar from chem. Now, something you may or may not remember from chem is that while these things form this bond, there is a certain distance that these nuclei like to stay apart, right? These atoms like to stay a certain distance apart, right? That distance we call the bond length. And for different kinds of atoms and different kinds of molecules, the bond length will be different lengths. For example, if I had a simple, normal carbon-carbon bond here, it's a certain length. If, on the other hand, it was like a double bond, remember we were sharing 4 electrons instead of 2, that actually will tend to tug these guys a little bit closer together, and they'll tend to hang out a little bit closer. A triple bond, I would imagine, would be even closer together. However, in different elements, and depending on what else is nearby tugging on them, the length might be a different length. But the point is, there's a certain distance they kind of want to stay. Remember that they're kind of being attracted together, right? They're trying to share valence electrons, right? And they're attracted to electrons, trying to fulfill the rule of octet and fill their outer valence shell, and yada, yada, yada. And so they don't want to be farther apart. They want to come together. But they don't want to get too close, because if they get closer, they're going to overlap even more electron cloud with electron cloud. Remember, negative and negative repel each other, so they don't want to overlap more. That also moves those really positive, right, 6 pluses here and 6 pluses here, nuclei closer together. And I'm pushing positives and positives closer together. They'll tend to want to repel. And so there's a certain distance where that attraction and repulsion electrical forces would tend to balance out. And that's where it would be stable, right? An equilibrium distance called the bond length. Now, does that mean it's impossible to push these guys closer together or farther apart? Well, of course not. You know that atoms are going to wiggle and jiggle, and they'll always be moving around, wiggling and jiggling. There's a certain distance they kind of want to stay, and they'll tend to oscillate around that position. But it is possible to move them closer or farther away. So now, say we have this tabletop, this surface, and we go and we put an object on it. It's going to push down. It's going to start to compress chemical bonds in the tabletop, and also bonds in the book here. They're going to get compressed. Now, if they get compressed, that's going to push these guys closer together. That's going to make them want to repel back, isn't it? There'll be an electrical force pushing them back, right? That force is what's going to push up on the book and support the book. Now, the harder I push down, the further I start to compress bonds, the bigger that electrical repulsion gets. As they get closer and closer, those electrical charges, they're going to repel harder and harder. And that's how the table knows how hard to push back. Now, of course, if I pushed hard enough, hypothetically, I could even push hard enough that I actually break the chemical bonds and break it apart and the table breaks. But within that limit, you see as I push harder and harder, I compress them closer and closer and make this electrical repulsion increase, and that's how the table pushes back. This kind of force from compressing those chemical bonds, you say we could go and analyze the force from every single possible little particle pushing on every other particle in this tabletop and in this book, or between the ground and the sled, or between the sled and the child. We could do that, but man, you'd take your entire life to do one calculation. Well, more than your entire life, thinking about how many particles are involved. It's going to be much better if we just take all the force from those particles being compressed and make one force arrow that we call a normal force. So, normal forces, they're forces that happen whenever surfaces are pressed together. If something's pressed into a surface, the surface pushes back with a normal force. Now, the normal force, it turns out that normal forces always act perpendicular to the surface. So if hypothetically I had an object on a tabletop here and I press it down into the tabletop would push back up on it, right? There'd be my normal force pushing up and it'd be perpendicular to that surface. I'm going to put a little N for normal force. If, on the other hand, that surface was slanted, maybe it's sliding down a ramp or sliding down a hillside, right? Yeah. Well, that normal force from the hillside will act straight out of the hillside, perpendicular to the surface. What if my object was on the surface of a sphere and it's sliding along? Well, at that point, that normal force, kind of in a line out from the center, would be perpendicular to the surface at that point, that normal force. In fact, it turns out that the word normal is kind of old-timey. Well, not that old-timey. It's geometry slang for perpendicular to. We talk about a line being normal to a surface in geometry occasionally. It means it's perpendicular to. That is why these are called normal forces. We don't call these normal forces because they're typical or usual or common, although they are. We call them normal because they're perpendicular to the surface. So here we have, getting back to our example, child on the sled being pulled along, faster and faster and faster to the right. We say, hey, we're thinking about the child. You say, what's touching the child? And you say, well, really just one thing. The sled is touching the child. So you ask, are those surfaces being pressed together? And the answer is yeah, the earth tugs the child down into the sled, so the sled's going to push back. So I'm going to draw a normal force on the child by the sled. It's going to start at the surface where the child is touching the sled, so on the bottom of the child, and it's going to push upward. So there is my normal force on the child by the sled. Let's talk about the sled. What's touching the sled? Well, you say three things. The child, the ground, and so it calls the ground? Yeah, the ground, and the rope. And so you'd say, well, first let's talk about the child and the sled. Are they pressed together? You say, yeah. So then the child, the sled is pressing against the child. The child's going to press back on the sled. There'll be a normal force on the sled by the child, shoving down on the sled. What about the ground? Are the ground and the sled being pressed together? You say, well, yeah, both these forces shove the sled into the ground, so the ground will push back up on the sled. There'll be a normal force on the sled by the ground. And there's my normal forces. Now the rope, that's not really pressing into the sled. That's going to be a different kind of force, a force along a rope or string or wire. That'll be a tension we'll talk about in just a little bit. So there's my normal forces. Again, I have got multiple normal forces in my problem, so I need to give them each a unique name, and that's what I use the double subscript, the on-by notation for. Okay, That's it. That's it for normal forces. Next, we can talk about friction forces. Once you have a normal force, you may have a friction force. It turns out it is absolutely necessary to have a normal force in order to have a frictional force between surfaces. So friction, when I was a wee lad, my teachers described friction as a force that opposes motion or something like that. But that's not really the best definition. It's better to think of friction forces as opposing sliding, right? And I can show you some great examples of that in a minute. But basically the idea is whenever two surfaces that are being pressed together attempt to slide past each other, a friction force will oppose the slide. That is the definition of friction forces. So, for example, the question I'm going to ask to spot a friction force is I will ask, are the surfaces trying to slide against each other? If so, there'll be a friction force opposing the slide. And it's always going to go along the surface against the slide. So consider, in this case, now I suppose I should comment on this. It turns out there are two main types of friction we're going to deal with in this class. There's what's called static friction and what's called kinetic friction. Have you ever had a really big heavy object like maybe a big heavy desk or a bookshelf or maybe like a dresser that's got a bunch of clothes in the drawer and you need to move it somewhere? And so you end up going to try to push it along. And when you do that, at first you push. And if you push real gentle, nothing happens. Right? And you say, well, why? I'm pushing this way. Why isn't it getting faster and faster that way? You say, well, there must be a force going against me balancing it out. And what's that force keeping it from slipping? Well, that's be a friction force. You say, well, what if I push a little bit harder? Well, it still doesn't slip, which means that force pushing against me must have gotten a little bit bigger. And I push a little harder and a little harder and a little harder on this maybe big heavy dresser, and it doesn't move, and eventually, finally, it will start to move. And when it starts to move, does it just kind of slowly start to creep? No, your experience, I think, with things like this, you push, and suddenly it's like it pops loose and it suddenly jerks along, right? It goes faster, faster, faster. It's like that friction that was pushing against you, it's like it suddenly breaks free, and that friction force like drops in strength. In fact, so that friction force, once it's sliding, it's different and it behaves differently. Once it's sliding, the friction force pushing against you is pretty much the same strength after that. It's like a constant force then. But before, when you were first trying to get it to move, that force could change. You push harder, it pushes harder, you push harder, it pushes harder until suddenly it slips. So there's really two types of friction. Static friction is what we call the friction before the surfaces slip. And kinetic friction is what we call the friction while the surfaces are sliding past each other. So there's two types of friction, static and kinetic. Without getting into too much detail, too late. Let's talk about drawing them on a force diagram. And so you would say, okay, well, friction, let's think about the child. The child, you said, there's a normal force on the child by the sled. So if those surfaces are pressed together, we can ask, the question we ask is, are the surfaces trying to slide against each other? And you would say, yeah. The child and the sled are trying to slide past each other. Here, check this out. If I were to yank real hard here, what's going to happen to the child? Well, the child will slip on the sled, won't the child? The child, in fact, would tend to slide off the back, right? The child would tend to slip backwards on the sled, don't you think? I know, you're thinking, well, you might think of it more as the sled pulls out from under the child, but regardless, compared to the surface, the child will tend to slide toward the back of the sled, which means the friction force opposes the slide. The friction on the child has got to be forward. Now it's going to act along the bottom surface, so I draw the arrow along the bottom edge. And I say, hey, this is a friction force on the child by the sled. Now, in this case, we are moving along faster, faster, faster together. That's the case I want to analyze. So the child isn't moving compared to the sled surface. They are getting faster and faster together. And so what kind of friction is this? It would be a static friction force. We could put a little subscript S to say it's a static friction. And a static friction acting on the child by the sled, just like the normal force was on the child by the sled. Okay, let's talk about the sled. Well, the sled and the child are being pressed together. There's a normal force on the sled by the child. So would there be a friction force on the sled by the child? And we would say, yeah. Which way is the sled trying to slide compared to the child? Well, the sled is trying to slide to the right out from under the child. And so friction on the sled has to oppose that slipping. The friction on the sled will go backwards to the left. So I'll draw an arrow along that surface to the left, and I'll say that's the friction force. It's a static again because we're not actually slipping here. The force between the child and the sled, we're not actually slipping those surfaces. So it's a static friction on the sled by the child, just like that normal force was on the sled by the child. Lastly, for friction, you say, hey, there's also a normal force on the sled by the ground. They're being pressed together. Is the sled sliding along the ground and they are trying to slip along the ground? And the answer is yeah. Not only is it trying to slip, it is actually sliding along, getting faster and faster and faster. And so that friction force, as we slide faster and faster to the right, the friction opposes the slide going to the left. And so I'll have my friction force on the sled by the ground. Okay, now which kind of friction is this? Well, those surfaces are actually sliding past each other. So that's a kinetic. So I probably should have done FK for kinetic friction on sled by ground. And that's my friction forces. Now, the last type of force we're going to talk about here today is tension forces. Those are forces whenever there's a rope or string or wire that's being stressed. Tensions are always going to pull, right? And they always go along the rope, right? So again, if I tug with this rope on my hand, the force is going to go right along the rope. It can't pull sideways to itself. And you can't push with a rope. We're only going to pull. And so on a force diagram, that means the arrow for the tension force will always go away from the system along the rope. Now the rope is kind of upward at an angle here. So I'm going to draw my tension force up at an angle. I like to symbolize tensions with a capital T. This is a tension force. Now, we will label tension forces. Sometimes people label them by saying, hey, what's the thing here that's tugging? So it's like a tension on the box by the rope. On the sled by the rope. But sometimes we'll talk about tension in terms of what's on the other end of the rope. So in this case, it'd be like, let's say this was an older sibling or something, a big brother or something. So it'd be a tension on the sled by the brother or something. So you can define it either way, tension on sled by rope or tension on sled by brother. A lot of times, if we have situations with multiple ropes, maybe they're connected to different things and it'll be more convenient to talk about what's on the other end of the rope to tell them apart. In this case, though, I'm just going to say on the sled by the rope. And there we go. Hey, that is all the forces in this situation. How do I know I'm done? Because I ran through my sequence of questions. I asked what range forces are acting. For this semester, it's only going to be gravitational. Anything that's near the Earth, you're going to have that gravitational force from the Earth pulling it toward the center of the Earth. And the Earth will interact. So I got those gravitational forces. I don't have to worry about electromagnetics. I don't have charged objects. I don't have to worry about nuclear forces because I'm not dealing with particles in a nucleus near each other. Next, we list what's in contact with the system because we're going to do contact forces. So I list everything touching. For example, for the child, it's just the sled. For the sled, it's the child, the ground, and the rope. For each thing that's touching my system, I run through these questions. So the child in contact with the sled. So we say, hey, are those surfaces, child and sled, being pressed together? Yes, that gives us a normal force. Once I have a normal, I ask, are those surfaces trying to slide? In this case, yes, the child is trying to slip off the back of the sled, so friction opposes the slide forward. And at this point, there's nothing else touching the child, so I know I'm done. I have all the forces because there's nothing else touching, we're done. And so I know I'm okay. Running through for the sled. Range forces, there's gravitational. Now we do contact forces. What's touching the sled? Three things: child, rope, ground. For each one, we run through in order. Child. Are the surfaces being pressed together? Yes, that gives us a normal force on the sled by the child. Are those surfaces that there's a normal force, are they trying to slide against each other? Yeah, the sled is trying to slip to the right out from under the child, so friction with the child goes to the left. Other thing touching the sled, we got the child done. Let's do the ground next. Are the sled and the ground pressed together? Yeah, then there's a normal force back up perpendicular to the ground on the sled. Sure, there it is, normal on the sled by the ground. Once you have a normal force, you can ask if there's a friction. The question is, are they trying to slide against each other? Yes, they are. The sled is sliding to the right, so friction goes to the left. And then lastly, you say the third thing that was touching it was the rope. When you have a rope or string or wire, the question you ask is it being stressed? In this case, it is. It's being tugged by that big brother or whatever on the other end, and so there's a tension force going along the rope. And ta-da! There's nothing else touching our system, so we're done. We know we have all the forces and haven't left any out. And so that's identifying forces and drawing them on force diagrams and labeling them. The next thing that's going to happen, just really briefly, just a peek ahead to talk about why we're doing these rules the way we are. What's going to come next is we're going to choose coordinate axes. Like, dealing with like X, Y axes, you might remember from class. The rule we use is the first axis goes along the direction of motion, and then the other axes go perpendicular to that. And so for our purposes here, the sled is moving to the right, so we're going to use coordinate axes that go left, right, and then perpendicular to that, up, down. It's traditional to call these X and Y, and it's traditional to call to the right positive and up positive, so I'll put a little plus sign in this quadrant to indicate that those are the positive directions. We can, if we needed to, it was more convenient or whatever, might choose to call different directions positive. If things were moving to the left, we might choose to call to the left the positive direction. But if there's no compelling reason to do so, it's probably best to use the conventional way of doing things, calling right and up positive. When we do things later with things moving along a hillside, then we'll want our coordinate axes to go along the motion, along the hill and perpendicular to the hill. When we do things going in a circle, we'll do it a different way there too. But for a while, this is what we'll be dealing with. Now, the point being that we want to link what the forces are like along a direction with the motion along the direction. We talked about that if the forces balance out, then we say it's in equilibrium and it'll be going at a constant speed. And if the forces don't balance, then it has to change its velocity in some way. So we'll want to think about forces along one axis at a time. So for example, with the sled here, or with the child, you say, let's talk about the forces up and down. Is the child changing speed up and down, changing velocity up and down? You'd say no, the child is just moving to the right, getting faster and faster left and right, but up and down, the child's not changing speed. In fact, if you had to put a number on it, how fast is the child moving up and down? You'd say 0. What about now? Still 0, still 0. And so in the vertical direction, the forces need to balance out. I have two arrows up and down, one up, one down. In order for things to add to 0, two numbers that add to 0 would have to be the same size, but opposite in sign, right? A positive and a negative. And so you say, oh yeah, look, an arrow up, that would be like positive, an arrow down, negative. Sure, and they got to be the same size. A way of showing that things are the same size, you might remember from geometry class, are putting these little tick marks or congruency marks on them. And that shows they're the same size. And we knew these were the same because two numbers that add to 0 have to be equal and opposite. So it makes sense we're in equilibrium. We're not changing speed up and down. However, left-right, you say, in this situation, the child and the sled are getting faster and faster to the right. Well, look at the arrows. Our force is left-right. There is a force to the right, and there's nothing balancing it out. So our total left-right force is to the right. It doesn't balance out, and so we're getting faster and faster to the right. That kind of makes sense. Okay, talking about the sled, I could try to do the same sort of argument for the sled. Look at the up and down direction, or left-right direction. But then you have this issue with this tension. The tension's not going up, down, or left, right. It's going using the words up, down, left, right, you'd say that tension force is going right and up. And so what we're going to do is we'll replace, for purposes of our analysis, we'll think of that tension not as one force like this. We'll think of it as being made up of two parts, two pieces, two components. A component that goes to the right, dot, 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 and a component that goes up, no, 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 no. So I make a chain of arrows that starts where the arrow starts and ends where it ends. Now, between the left-right direction, the up-down right, and the up-down direction, that of course is a 90-degree angle there. I'm making a little right triangle. Say this angle, we'll say that angle has a size. Let's give it a symbol theta, Greek letter theta, to represent the size of that angle. Then I can identify how long these sides are using a little right triangle trigonometry. So, for example, I'm not going to go into details at this point, but we'll say this side would be the tension on the sled by the rope. That's how long, these labels, by the way, this is a variable saying how big this force is. Well, this side is going to be that hypotenuse of the triangle times the cosine of theta. And this side would be equal to the hypotenuse, the length of the hypotenuse, tension on the sled by the rope, times the sine of theta. Now I can think about my up and down forces. How many up and down forces do I have? 1, 2, 3, and then this piece of a force over here. 4 up and down arrows. Is the sled changing speeds up and down? You say no. As it slides along, it's changing speeds to the right. It's getting faster and faster. However, up and down, the speed is 0, still 0, still 0, the vertical speeds. And so we can say that the forces should add up to 0. But you say, look, there's 1, 2, 3, 4 arrows. Can I mark any of these arrows as being equal length? You say, no, I just know that this and this together have to add to the same value as this and this going down. The only way to show that these arrows add up to 0, you can't show it with tick marks. The only way to show it is with an equation. And so we'll talk about adding up all the forces in the vertical direction and say they need to add up to 0. And we'll call up positive, so my force is up minus my force is down equals 0. So I might write this as the normal force on the sled by the ground going up plus that component of the tension on the sled by the rope times the sine of theta, that's how long this side is, minus going down, normal force on the sled by the child minus the other force going down, gravitational force on the sled by the earth. Those are going to add up to be a total of 0, my ups and my downs. So this is just an example of how we're going to get an equation from the force diagram. So it's really, really important that our force diagrams are right. If I'm missing an arrow, it's going to mess up all my calculations after that. And we definitely care about the angle and the direction things are going. The direction is going to determine whether these are positive or negative values. We put the sign for direction on in this step when we add up the forces. And so it's really important that these are arrows always. And of course we had to use the angles and stuff to figure out how long these sides were with a little trig. So there's these rules for how we do force diagrams. They're there for a reason, and it's going to be so that we can actually use the diagrams to solve problems and figure out missing forces and things. You'll see as we go on that force is really the central concept in mechanics, which is the large field of physics that we're studying this year. Now, I could go through and do a sample problem. I have another video doing that, which I'll refer you to, but this is kind of my first overview of forces, identifying forces and drawing force diagrams. And along the way, I touched on some important ideas about like definition of a force and the idea that we're thinking about forces along coordinate axes, the rules for how you set up your coordinate axes. First axis goes along the motion, this other axis goes perpendicular to it. And about drawing components in, making a chain of arrows that go along your primary directions here, along your coordinate axes, in this case right and up. So it's a chain of arrows that starts where the arrow starts and ends when it ends. Yep, and that's really the bulk of this. Being able to do force diagrams, this is like generally, kind of as I was indicating here, solving force problems is a huge part of physics. We start with a sketch. We choose our system, the thing we're going to analyze. In this case, we analyze the child and the sled separately. Draw force diagrams, also known as free body diagrams, for each object. On the free body diagrams, we represent the object simply. We draw our forces as arrows, starting where the force acts on the object and showing the direction that this object is being pushed or pulled. We have questions to help us identify our forces, and we label each one. Each one has its own unique name. We use the double subscript, the on-by notation, to do that. Then we choose coordinate axes, break forces into components, like we did with the tension force here, and then we can plug into the sum of the forces is 0 if we're in equilibrium in an axis. After that, we'll do some math. If we know enough values here, we can solve for missing values. And that's basically how it works. That's the main gist of this unit. So, of course, you can always email with questions or bring your questions to class. Hope this was helpful.